So welcome back, everybody. And the topic this week is to try to wrap up the discussion we've been having about logistic regression. And as I said last time, this is going to serve as a stepping stone towards neural networks, which is going to keep us busy for quite some time now. So I'm going to repeat some of the things which we discussed last week. And then we are going to look at the coding examples. And when we are done with the code examples, we are going to start looking at the basic structure of neural networks and how to program them, how to set them up, and all these technicalities. And this is going to keep us busy in the next 4 or 5 weeks. And it will also be the central theme of project number 2. So this is the basic outline of today's week. The material which we will cover with neural networks will also serve as a way to introduce automatic differentiation, which we will discuss next week when we are setting up the program and the algorithms for designing a neural network. And hopefully the exercises will also be of use because we are going to build up gradually a software for a neural network. There are some videos here, and also for the lab sessions. As we also discussed last time, there are no exercises this week. There's only a focus on wrapping up the project. And the deadline is next Monday. And we always have a kind of extra day roughly. So we never start grading seriously before 1 day after, because we know that something may always go wrong, during the handing of the project. Sometimes we had the network going down, there was a thunderstorm and the network was unavailable and people couldn't upload their projects, etc., etc. Things happen. So there's always some 24 hours after you have handed in where you have the possibility to correct and improve upon the project. So in a sense, there's an extra day. Okay, so what I want to do now is roughly to go through things via the whiteboard. You have most of the information online here on in the Jupyter notebook. So from last week, what we discussed was actually the first case of a classification problem. And we are going to look at some of the basic mathematics which we studied. And the case which we studied last time was what we call a binary classification problem. So a binary classification problem is a typical yes, no, true, false, or that you have encoded everything as zeros or one, or you could have -1, +1, etc. So it's a binary case. Let me remind you about some of these things, because the logistic regression equations is the first encounter after lasso regression where we don't have an analytical expression for the parameters, the unknown parameters we want to train. And in this case, as in basically all cases, except for simpler cases like ordinary least squares and ridge regression, we simply cannot find an analytical expression and then solve it easily. So there is an analytical expression, but we have to solve it numerically. We did actually solve it numerically by matrix inversion. So in a certain sense, we do have analytical expressions, but you have to, in this case here, solve them numerically by some gradient descent. In the case of ordinary least squares and ridge regression, we had a nice expression where we could just obtain the parameters by matrix inversion. So I'm going to go a little bit back to the whiteboard in order to slow down the pace. And we are going to revisit some of the equations and the basic philosophy. And then at the end, we are going to look at ways by which you can implement this numerically. Now, project number 2 is actually going to include logistic regression as a coding case. And you will also see that logistic regression, the way we are going to set up the equations, is going to correspond to a neural network without any hidden layers. But we will come back to that. So let's go back to the basic mathematics of linear regression, and no, sorry, logistic regression. And now I just wanted to switch back to the whiteboard. So one of the basic approximations we did, since we're dealing with a classification problem, is to now assume that the data which we have, which we label with a y of I, which is the target or output value, is now given by a probability distribution plus some noise. So this P of X now is a probability distribution, and it means that we often assume that this is normalized. So if we integrate P of X, D of X, where X is defined in some kind of a domain here, this integrates up, it's normalized to 1. We also know that the probability of P of X of I is smaller than the probability of P of Xj if this X of I is less or equal to X of j. Secondly, we have something which is called the cumulative function or the cumulative probability. Cumulative probability. I'm just quickly repeating some of these basic concepts from statistics and probability theory. So I'm writing this as an uppercase P, so P here, P of X. Let me just write this a little bit nicer. So we have an uppercase letter A, P, and this is now given by if X is defined from minus infinity up to plus infinity, we integrate up to a variable X. So we have an X prime over dx prime. And the cumulative function is also something which defines a probability, and it can be used later when you want to change from one probability to another one. But these are technicalities which we'll leave out. So as an example, suppose now that the X is defined between a variable A and a variable B, that's a domain. Often you will find X being defined from minus infinity to plus infinity, like a Gaussian. In this particular case, what you have is that P of B is set to be equal to 1. Then with the probability, you can calculate expectation values as we discussed. And if we just remind ourselves of that, we know that we can calculate the moment of X, so X to the power of N. This is simply defined as X in a domain D, and then we have some X of N multiplied with the probability of P of X, D of X. So these are typical expectation values, which we will be calculating if we know P. Just a quick reminder is that normally we don't have access to P in many of these machine learning training examples, which also means that we end up calculating what is called the sample mean value. But this is kind of general expression if you have a continuous distribution. Now, if we now look at a typical output of a binary problem, so a typical output of a binary problem. Binary problem is a case where we have y of I equal to either 0 or 1. So that's a typical example. Now, if you have cases like true, false, or other values, it's pretty common to convert them to numerical values, so that's much easier to deal with in your codes. So that means that you would typically encode, let's say, true, false, like 0 and 1s. In case you have -1, +1, it's often pretty common to rewrite them as 0 and 1s. Okay, so this is a typical output which you would use in your training. Now, the X values can take many, many different values. So we would have a domain of inputs and outputs, so which we now just call D, and we shouldn't make a confusion with this one because this one just is a D which is reserved for the X's. But in our case now, D contains all the possible events which we have with input values X0, and then we have Y0. we have a new set x1, y1, and this goes all the way up to the final data point, xn minus 1, and then we have yn minus 1, like this. So every y value, all y values are given by either 0 or 1, if this is our choice. Okay? And then we want to make a classification. We want to train a function P, which is our probability distribution, and we can then choose model for that. And so let's look at the kind of distributions which are used quite a lot in this type of examples, classification examples. So it's okay if I just change page? Everybody fine? So if we now look at the typical data case, which you could encounter, so you have some x's here, and suppose now that x lives between 0 and 1. So we have 0 here, and we have 1, so this is just an example, and y takes the values 0 and 1. Actually, I should put equal to here. So we assume that x is a continuous variable. And we then have observations of y. So the crosses here are the observations. And then I'm going to write the 1 here. So we have 1, and here we have y. And then we have another set of observations here. So these are the observations which we make as a function of x. So what is pretty common then is to try to fit a function p. So we would make something like this. So this is our function p of x, which we want to fit. And typically, what we would say then, if we put the half here, a typical case, so you're not constrained to use that, and you will see that when you come to multi-classes, like if you're going to predict numbers between 0 to 9, which is a famous data set called the MNIST data set, then you have 10 classes, 0, 1, 2, up to 9. And these will be handwritten numbers which you want to recognize after you have done the training. So if we now look at these more simpler cases, what you could say is that y is equal to 0 if p of x is less than 0.5. So you're putting in a threshold, and y is equal to 1 if p of x is larger than 0.5. And obviously p in this case is smaller or equal than 1 and larger or equal than 0. So this is a typical function which we could now fit in a logistic regression machinery. Okay? So this is just a reminder of what we did last time. So let's now look at a typical function. So a typical function which has this property is what's called the logistic function, or the sigmoid function, or just the logit function. So function P. So you will see this being called the sigmoid, the logit function, etc. And this P of x is then given by a function which goes like this, e to the power of x, so 1 plus e to the x, and this is equal 1 or 1 plus e minus x. So what you could say now is the following. So we are making a model where we now want to train this function here, where we have some unknown parameters theta. So we would have a y of I, which is given by p of x of I plus epsilon of I. And we would typically just call this a p of I here. And now you could say that if y of I is equal to 1, then p of I is just equal to 1 divided by 1 plus e to the minus x of I. And then if y of I is equal to 0, then the probability is equal to 1 minus this function here. plus e to the minus x of I. So we have only two possible events. So it's a discrete set of events. That means that our probability function must reflect either the probability of getting y equals 0 or y equal to 1. And since these are only two events here, then what we have to have is that the total probability, if I'm summing up now, in this case, it's I equals 0 up to 1. So I have P of I, which is going to be P0 plus P1 here. And 1 is now referring to the case that Y of I, so it's a little bit clumsy notation. So this is Y of I equal to 1, and this is Y of I equal to 0. And if you sum the two here, you will then see that this adds up to 1, as it should. So this is a discrete set of events. So keep this in mind. X is a continuous variable, but the Y's, which we are interested in, are now discrete events. And that means that the probability has to be a discrete probability. Okay? X is continuous, Y is discrete. So that's a big distinction from when we did linear regression, where we actually assume that Y is given by a continuous function. So what we did next then was actually to try to define a probability distribution which reflects all these possible events in the domain D. But before we do that, let us quickly remind ourselves of the graphical representation which we are going to use again and again here. So let's now just remind ourselves about that. So there are some elements of repetition from last time. So this is the graphical representation. And in this specific case, what we are going to, or the way we are going to label things is an x of I. This is one of the variables we're dealing with. And we would simply call this the input layer. And we are going to use that one, this naming, when we discuss neural networks as well. Now, this is now fed into a function, which I'm just going to call sigma. It depends on x and some unknown parameters theta. This is actually in this specific case, which we are going to do now. This is, in our case, this is going to be here. This is going to be P of X of I. And then there are some unknown parameters, which we are going to specify. So, but we can leave this a little bit, how to say, undefined, except that we are going to call this for an activation function. So this is a function which receives an input and it activates a threshold output. So in the literature, you will find that this box here, or this function, is normally called an activation function. And what you also would call this is a node, or later we are going to call this for neurons or units. And this is very much inspired by the way people thought that neurons in our bodies or in our brain would respond to an external signal. So there comes in a signal, and then depending on the strength of that signal, you output something. And in this case, there's going to be a threshold function, but we are going to collect later, we are just going to collect these two boxes into one. So in this particular case, we have some function that if it's below a certain value, so we would typically call this a threshold. This, it produces an output. And we are just going to label this output like this. So this is our output layer. Now, this output layer, or this result here, is going then to be fed into a new function. So when I'm feeding things into a function, I'm going to write square boxes. And in our case, this is going to be our cost function, which then will depend on y tilde. on y, and also theta, the parameters. And in here, we are going to feed the target values. So this is our target or output. Now, I'm going to take away this threshold box, and I'm simply going to call this an activation layer on activation function. So you can think of the combined action here of this function, which you're feeding in a value to, produces an output. And then there is a threshold which says that if the value is beyond a certain value, it returns 0. And if it's above a certain value, it returns 1. Okay? Does this make sense? This has actually a name in the literature, and it's called a perceptron model, the simple perceptron model. And that is motivated by research from neuroscience, where one thought of this a mathematical representation of the way a neuron fires a signal. A neuron receives an input, and then it sends an output. And depending on a threshold in the potentials which they are being activated by that specific neuron, it spits out either a signal or nothing. So this is the way you can think of what you have here. And this is normally called a simple perceptron model. And you will find that as a recurring name in the literature. For us, what you have here is actually nothing but a graphical representation of the mathematics which we are implementing now. So we can simplify this in the following way, and this is the way I'm going to draw it from now on. So simplified, we are going to have an input x of I. This is our input layer. And then we are going to have an activation function, which will depend on x of I and theta. And then it produces an output, y of I tilde. This is the output layer of the model. So this is a model which we are making. You could have done exactly the same with ordinary least squares or ridge regression or lasso regression. There is no difference here. And this feeds into the cost function, which is now a C, which depends on yi or yi tilde and the parameters theta, and it receives the target value here. And then the cost function is the one we want to optimize. So the problem itself, which we want to solve now, is either a maximization or a minimization with respect to these parameters theta of this function C of y tilde of y and theta. This is as before. So we can also take a maximization. Now, since we are devising probabilities here, what we want now is the probability for the whole domain of events. So we want to train a probability which then reproduces the whole set of possible outputs. Now, just a small digression here. So this was the case where you have just a scalar coming in, but in our case, we are actually going to have a design matrix. And this will have different features, and every column represents a feature here. So we have an xn minus 1, p minus 1. We have an xn minus 1, 0, x1, 0, etc., x1, 1, all the way down here. So that means that if we now pick a specific column, row here, xi, there's going to be an xi0, xi1, up to some xi of p minus 1 here. If we now single out this one, this is going to produce a single output y of I. So if I now look at the network which I set up, then my input layer would be some xi0, xi1, down all the way to xi of p minus 1. And these feed into this function sigma that produces one single output, yi, because we're looking at a binary case. If you have a multi-class problem, you can actually spit out, let's say, 10 outputs. If you want to classify numbers between 0 and 9, if you feed in handwritten figures or handwritten pictures of the numbers 0 to 9, then you can train a model to recognize these figures. And then next time you feed in 1, you want to see if you can recognize correctly what kind of number it is. So in that specific case, these x's would be the pixels of an image. So you would then feed in all these into this function. And then you would produce an output, which is then fed into the cost function. And then you compare that one with the data you want to test. This is the target. This is in the case of a binary class, because then you spit out either 0 and 1. So your model is producing one value. And if your target value is 0 and you produce 1, then you are predicting the wrong result. But just think of this, because you can have many features which then decide or define the data set. So in project number 2, we are going to look at, for the classification case, we are going to look at more realistic data. And that means that we will have a design matrix, which then in each column will represent some specific feature of the data set. Okay? Any questions so far? So I'm repeating some of the things from last week, just to give you the kind of general structure which is going to come when we look at neural networks. And you will see very clearly now why this simple logistic regression is going to function as a stepping stone towards a neural network. Yeah, there's a question here. Yeah. Oh, so sigma here is actually the activation function for all the x's now. Could you say it again? Yeah. Yeah. Okay. So this, if I understood you correctly here, let me just, I should actually write this out in more detail. So this is going to be a function of, I just write x and the parameters theta, which we haven't specified yet. Yeah. It's an I. Yeah, yeah. And this is a semicolon. Sorry. Thanks for pointing that out. I try to make my handwriting a little bit better. So the function, the simplest possibility now is actually to define simplest case. So we would have one feature. And what you will see now is that it's pretty common to actually include what we call in ordinary least squares for the intercept column. And you will see that quickly now, because we will define something like a P of X of I. And this is one of the simplest models you can think of. So we would have a 1. So this is the sigmoid function plus E of minus. And then I have a theta 0 plus a theta 1 times X of I. But in principle, what I could have is something which has many more features. So I could have 1 plus E to the minus, and then theta 0 plus theta 1 times X of I, plus theta 2 times X of I, up to some feature theta P minus 1 times X of I. So if you look back at that design matrix which I put up, that is a typical example of where I can have every column representing a specific feature. Okay? Now, the next thing which we did last time, and I'm just going to repeat some of the results from last time. So let's do that before we move into code examples. So what we did then was to define this as a probability. So we have the domain D of events, the variables theta. This is our cost function. And some time ago, what we did was simply to write this as a product of the individual probability when we assume that every event here is independent of each other. So this is what we did some time ago. But what we did last time was actually to replace this one, in our case, with that probability P of I to the power of Y of I, which is either 0 and 1, multiplied with the other possibility. So now these probabilities represent discrete set of events. And then we had 1 minus Y of I. And just keep in mind here that Y of I takes only the values of 0 and 1. And we said that this P of I is the same as 1 divided with 1 plus minus X of I. So what we are doing now is that for every Y of I, which can take either value 0 and 1, we are using the properties of what's called a binomial distribution. So we have the possibility to take into account both types of outputs. And you see now that if Y is equal to 0, then if Y is equal to 0, then we have simply P to the power of 0, which gives us 1 here. And then we have 1 minus P of I as a probability. If Y is equal to 1, then this is P of I equal to 1, which then gives us this expression. And this term here is simply 1. So it's a simple way by which we can bake in the probability of this binary case. Now, to calculate the derivatives of that case, because we want to maximize this function, so what we want to is actually an argmax. We don't want to have a marginal probability, but we want to maximize the probability. Then we simply want to calculate the gradients of this function, where this is the product of all these probabilities. Now, as we discussed last time, this is a little bit clumsy. So what we normally do then is to maximize the log of the probability or minimize minus log of the probability. And that gives us much nicer equations to deal with numerical. So let me remind you of those equations. And this actually ends a little bit the discussion we had last time. So when we then set up minus log, so what we ended up doing was to set up a minimization problem. And this function, which we're going to minimize since it's a log, it's by definition a convex function for the domain D of theta. And what we found then is that this is equal, this minus log of P of D of theta is equal to minus, and then I have a sum over I equals 0 up to n minus 1, the data points, Y of I. And then I have log of P of I. And then it's plus 1 minus Y of I times log of 1 minus P of I. Then what we did was to calculate the gradients. So we calculated the gradients, and then we took a dc of d theta. And this gave us minus the design matrix times a vector y, which contains the target values, minus the probabilities p. So p and y, they are vectors of length n, so they have n elements. And x is our design matrix, which has dimensionality n times p. And then we see that when we multiply these functions with each other, the matrix times the vector, we get the derivatives or the gradients, which have length t. So this is something which we went through last time. And the thing which I wanted to emphasize to you is then the following. So this dc of d theta, let me just remind you of that one, is something which I'm just going to call the gradient of theta. and this is a vector of length p with p elements. We could also calculate, so theta is included in p, since p is a function of x and theta, x of I and theta. Then we can also calculate the second derivative, and if we do that, dc d theta, that is going to be a matrix, which is our Hessian matrix, and we have that one multiplied with a matrix W, and this W depends on theta. And this W has matrix elements for the diagonal, which are given by P of I of 1 minus P of I. And then I have Wij equal to 0 if I is different from J. So we have two quantities which both depends on the value of theta. And the way we're going to solve this is by gradient descent. This is the way we're going to find the update of the parameters. And this is roughly where we ended last week. Now, one of the reasons why I repeat that much is simply because I want to link this with a setup of neural networks which come after the break. So let's take a look at the final equation which we end up coding, is that if we want to set up and find the value of theta of n plus 1, this is going to be given by the previous value minus, and it's going to contain H, the Hessian matrix. Let me just bring that back again. This is called the Hessian, and it's a function of theta and x, obviously. So it's going to contain theta of n, and it's going to be multiplied with a gradient, which then is a function of theta of n. As we have seen repeatedly in project 1, we are going to replace this with a learning rate. So this is going to be given by theta of n minus an appropriate learning rate times g of theta of n. And this is the way we are going to find the solution to the standard logistic regression codes. And in project number 2, we're actually going to start the project because we want you to also read in a data set, and then we are going to reuse the gradient descent algorithms from project 1, except that now you're going to change that with a new cost function. That's the only thing which will change. And that is going to also motivate what comes next week and the week thereafter, the usage of automatic differentiation, because you can simply just change cost functions and new activation functions. And with automatic differentiation, you can just have a general code which just plugs in the gradients. So that's why we did insist a lot on having a gradient descent code which functions in project 1, because this is a kind of working horse for essentially everything else we end up doing. So this was a typical example of what we are going to set up. And what I wanted to give you before we take a break is a set of examples you will also see in the lecture notes here. So after the break, we are going to run through some codes and then go back to the whiteboard again. But let's take a look at the examples which we are going to study. So one of the examples is a so-called, and some of you may have met that. So this is an OR gate. So this is back from electronics. So an OR gate has inputs which go like x1, x2, and then it has an output. So if it has bit 0 and bit 0, the output is 0. If it has bit 0 and 1, so these are bit 0s and 1s, so it's a binary system, it has an output 1. If it has bit 1 and bit 0 here, it has an output 1, and 1 is equal to 1. Okay? It's either 1 or 1 and 0, so you maximize it. So this is a typical gate which you will encounter if you do electronics. Have you encountered this in some different courses? You can just look at this as a case of an input and an output. Now, if you look close at this, let's call this output for Y. If you look close at this, and I plot X1 here, and X2, 0 and 1. This is a classification type of problem. And what I'm going to say now, if I have, so X here means 0. So X is equal to 0. And a circle is equal to 1. So if I have X2 equals 0 and X1 equal 1, then I get a circle, which is a 1. And then I get a circle and a circle. Now, so let me ask you now, and I want to trigger your intuition here. Could I use a line fitting here to separate the two cases? Yeah, I could actually use linear regression. There's no problem. And you will see that in the codes that linear regression does a nice job here. So I could now fit a line which goes like this. And if I have that line, I could say that if the value is below the line here, then I give 0. If it's above, it gives 1. So I could make a simple model now. So model where I simply have yi is equal to some x1 for case I. So I have some data sets, and I have an unknown parameter, which I'm called w1, plus an x2 of I, the data set I, which corresponds to the output y of I, plus some parameter b, so which now could be the intercept. So think of b as an intercept. And then I want to fit these parameters w1 and w2. And then if I can fit them, it should give me a line which separates the two cases. And if it's below a certain value, you get 0, above it's equal 1. Does that make sense reasonable? And you will see in the examples, if I do logistic regression, I'm actually going to get a result which is decent. So if I do now logistic regression here, if you look at the data set, I would now have X, which is just given by a set of vectors, 0, 0. This is the first case. And then I have, so X1 and X2. And the next one is 0 and 1 transpose. So these are drawn as, or written as vectors now, T. And then I have 1, 1, T. And then I have my Y zeros. So if I have Y equal to 0, then what I should have then, let me just write like this. If Y is equal to 0, what I have then is 0, 0 multiplied, and I'm writing this as a vector as an inner product, plus B. If I have Y equal to 1, I have 3 options. In that specific case, I could have 0, 1, but I could also have 1, 0 and 1, 1. So I'm not going to write all of them, but this is what I would have to train. And then my design matrix, I would now define parameters, which I need to define. So the parameters which I'm going to find is B, which is going to be the intercept, W1, and W2. So these are the parameters which I want to define. And that gives me a design matrix. So I'm going to give you the results here. So X is then going to be given by 1. This is the intercept. I have 4 cases, 0, 0, 0, 1. This is 1, 0, and 1, 1. So this corresponds to B. That's the intercept column. This corresponds to the X1 feature, and this to the X2 feature. So I got so obsessed by linear regression that I want to use it everywhere. And now what I'm doing is to specialize this discrete case to linear regression. And I want to fit a line which just separates the two cases. So if I do that fit, what I'm going to get then is the following. So I'm going to get theta, the variables are given by 1 divided by 4. So you can do this by hand almost. And that means that y theta, the prediction I make, is x. So this is just linear regression, ordinary least squares. So I'm just taking x transpose times x. I invert it and multiply with x transpose and y. So this is a pretty straightforward exercise. If I do that, what I'm going to get now is 1 divided by 4, 3 divided by 4, 3 divided by 4, and 5 divided by 4. So that's my prediction. So what I wanted is 0, 1, 1, 1. So this is my y. And now you see that what I can do is to say the following. If my result is 1.4, I put it to 0. And you can see now you could actually put a threshold. If it's below 0.5, you put it to 0. If it's above 0.5, you put it to 1. So you're not going to get 0, 1, 1, 1, but you will get a set of numbers which you can interpret. And then you will set a threshold. So typically here, you would make a figure where you then would make a prediction. So you have 0 here and 1 here. And then you would simply say now that if, so suppose now 0.5, if it's below 0.5, below, then predict 0. And then above, predict 1. Okay? So these are the kind of examples we will look at after the break. So I'm going to give you another one before we take a break here. And this is the case which you will not be able to fit with linear regression or logistic regression, but you can fit it with a neural network. And that is the more difficult case of an XOR gate. So an XOR gate is now, and this is what I'm going to write here before we take a break. So this is 0, 1, x1, and then I have x2 here, 0 and 1. In that case, what I'm going to get is 0 here, but I'm also going to get 0 here. And then I have 1 here and 1 here. And now you see that there is no way you can fit a line which separates well all the cases. So this is an XOR gate, and you will see in the examples that this is the first case, a very simple case, which we will not be able to find a line which separates the results. Logistic regression is going to fail, but neural networks are not going to fail. And that is linked with something which is called the universal approximation theorem, which we will start with looking at after the break. So I went a little bit over time because I wanted to have this before we start looking at codes, and then we go back to neural networks. So this week, we want to start the discussions of neural networks, but we are going to link this with logistic regression as a first stepping stone. So I went a little bit over time again, but then we take a 15 minutes break, and then we're just back at 15:20, if that's okay. Eh? So what we did before the break was just to warm up a little bit and look at the basic approach, which we are going to do when we now want to encode logistic regression. So let me just quickly remind you of some of these small technicalities which we looked at. So the basic thing which we are going to do now is to set up a model where we are going to define these probabilities in terms of a binary model. And in our case, the probabilities are going to be given by this standard binomial formula. We are going to look at a binary case, but in the lecture notes, you will also find the case of a multi-class system. So where we have just more than just two classes. Now, the binary type of classes is one of the most common ones, which you will encounter everywhere. Many of the data which we look at are typically yes, no, true, false cases. This was the first step. Now, the problem which we have now when we have this function and we take the derivatives is that these derivatives will have to be included in a gradient descent solver. And the program you will see in the lecture notes in the Jupyter notebook is actually an example of that. So we're going to set up a gradient descent of this type here. They're going to be a learning rate. And we're going to first set up a simple data set. Then, after we've gone through the simple data set, we are going to look at these examples. And I'm going to show you that you can fit these with standard linear regression, the OR gate. You can fit that with logistic regression. But then when you come to the XOR gate, where you cannot define a plane which separates the different cases properly, then you will see that logistic regression and linear regression are going to fail. So let's look at codes. And then when we're done with that, we are going to go back to neural networks. So let me just bring this back again. And so the beginning here is actually just a repetition of what we went through. I wanted to repeat some of these things so that we have everybody with us. There is an example here which we will postpone the discussion of till we have entered the discussions of neural networks. But this is the so-called multi-class case. And there is a function which looks very much like the sigmoid function. It's called the softmax function. We are coming back to this one. So now we're just going to mainly focus on the binary type of problem, okay? So the optimization part we're going to look at now is actually to solve these equations, where we obviously have replaced the second derivative with a learning rate, okay? So let's scroll down a little bit. There's an example code here, and I just wanted to show you how you can actually write your own code. So I just call this a class logistic regression. And remember now that one of the things which we did before the break, when we looked at this logistic function or the sigmoid, we actually added the ones, the intercept. So let me just scroll back a little bit here. If we go back here, you will see now that there is in the typical model, there's a theta 0. So the simplest case now is just to have one feature, theta 1, but then we have an intercept column. So we have to bake that one into the design matrix. And you will see in the code here that there is just an add intercept column to feature matrix. So I'm just going to dampen this volume a little bit. Then you will see that I have included the sigmoid function. So that's going to play the role of an activation function. I've also included here the softmax function. We are coming back to that one when we discuss neural networks in more detail. But this is a function which has a complete logistic regression case where you can have a typical with the sigmoid, yes, no, or a multi-class case where you could have 10 classes you want to classify. And each one of them gets a probability. So the softmax, in a way, is nothing but an extension of the sigmoid function to more than 2 cases. So this is the way you can view it mathematically. Then if you go down here, you will see I add the intercept column. And I'm setting up here whether I have a unique classes, more than 2, or if I just have a binary case. So if we just scroll down and look at the binary case, which is the one of more interest now. So if my Ys have not been converted to 0 and 1s, suppose now that when you read a data file, it just says true, false, or something similar, yes, no. Then we are converting them into 1s and 0s, because else it's very difficult to set up a probability and then say, if your data says yes, no, and you want to spit out either 0 and 1 in case you have 0.5 or above or below. So that means that there is a conversion here where I now convert this into zeros and ones. And you could actually, in many data sets, you can actually do that when you start reading the data. So we will see that next week when we look at some real data, which we are going to use in the project, where you will have the data which needs you to actually convert it into ones and zeros or whatever. So this is something which we always have to do, to look at the data set and see if the data is set up so that we can read it easily. When you use pandas as a library, that often does that job very easily for you. So then, if we now just scroll down here, you would now see the definitions. I define the probabilities, and I spit out values. But if we now go down a little bit, so let me just run, this is just the beginning of it. And then I have the evaluation metric. So I have a binary cross entropy. And then for the softmax function, there's something which is called a categorical cross entropy. This is my cost function. So this is nothing but the function which we put up in the lectures, where you have these logs multiply with each other. If you look at the expression here, this is what we plugged into the in the example before. So I'm just gonna run through only the binary case. I'm going to generate binary data, which is just given by some Gaussians. And I have a multi-class data as well, which I can generate. But then if we go back a little bit and you look at the, so let me just run back a little bit here. You will now see my essential part, which is the gradient descent, and that's this one. So epoch here, this is plain gradient descent. So epoch is the same as iterations, like you have implemented in gradient descent. With stochastic gradient descent, you put this to epoch, but now this plays the same role as my iteration here. And you can see now that I set up the probabilities with the sigmoid function. I calculate the gradients according to that formula, which you saw in the lecture notes and which we discussed before the break. This is now the new weights. So it's just the previous values multiplied with the gradient. And then every time then after 100 iterations, I print also my cost function if we want to. Because you want this to drive this cost function, obviously, to a minimum with the optimal parameters. So the heart of the code here is actually the one you see here. This is your gradient descent. But now the gradient descent applied to another cost function and obviously another gradient. Yeah.
I didn't quite get why you only computed the loss for every 100.
No, because I want to print it out every 100.
Okay,
so
you just print it.
Yeah. So you don't want to print it out every iteration, right? So the you can actually print that out at the end if you want to, or you can just look at how it progresses. So the whole point here is that in next weeks, we are going to replace. So one of the reasons why I put in the cost function here is that we are going to define that one, and then we are using automatic differentiation, which then will simply set up this expression for the gradients for us. And this is one of the things which will make life much, much easier when you're coding a neural network in project number 2. But this is essentially the heart of the method for logistic regression. And if you look at it, it's not that different from what you did in project 1 on lasso or ordinary least squares or ridge. Except the only thing which changes is the derivative here and the cost function. Okay? So the gradient descent is in a certain way almost agnostic to the type of derivatives you have. You just need to feed in the derivatives. So if I run this, and I think I run, so we have the accuracy score, which is a typical score. You can calculate the cost function. If you look at the accuracy score, that simply counts the mean value of the number of correctly predicted events. Now, this case is a vanilla data set where I just make classes with Gaussian distributions. So it's a very easy thing to train. And if I now just run through it here, you see now that the binary classification has an accuracy of close to 100%. And you can see the cross entropy loss, which is 0.01. And same here with the multi-class classification, it's getting pretty close to 100%. And keep in mind here that they haven't done any scaling of the data, no nothing. This is a simple vanilla case. Now, there is another set of data here, which we, actually, this is a little bit more delicate because this is a data set which has been studied a lot, but we have taken away some of the emphasis because it deals with analysis of breast cancer. So it's a model of Wisconsin breast cancer data where the output is either a benign tumor or a malignant or not benign tumor. And this is typically coded as ones and zeros. So the data set here, the benefit of this one is that you don't need to stress with setting up the train test and so on, because the data set is included by default in scikit-learn. So scikit-learn does all the setup for you of the cancer data and the target values. So these are the X values and these are the Y values. So it does it automatically. Now in project number 2, we're actually going to be, to force you to actually read in the data and set it up properly. Okay, so in this particular case, and here there is no scaling, which we are doing here. And in this case, you will see now that the data is split into, it has 30 features, and it has 426 patients in the training and 143 in the test data. And in this case, logistic regression, and the data is actually evenly balanced between yes and no. And it gives a pretty good total accuracy. So you make a prediction, a correct prediction here without any scaling, any fancy things you can do with logistic regression. So this is actually reading this data set and plotting and performing the calculations. You could have used the same code which I showed you previously, or you can use scikit-learn. So this is also a useful case to test when you're running your own codes. And you see that the scikit-learn, the only thing you need to bake in is to import logistic regression here. And this is a data set. So I'm not going to talk too much about it because some people may actually have bad memories if you've gone through it. So I'm sorry for that. The other thing which you can do, and the scikit-learn has a lot of functionality here, where you can load the data and you can also analyze the data. So you can, for instance, make a plot of the data. And I just wanted to show you. So some of the features is actually the mean radius of the tumor. So this is something which is a pre-analysis which you can make to gain more insights about the data sets. And what you see now is that the mean radius separates cleanly a bad case from a good case. And you will see then that for the mean radius and the mean area, the mean perimeter, so these are some of the 30 features which a pathologist would typically pick out in order to classify a tumor. So actually, for medical applications, machine learning plays a fantastic role. So you're probably familiar with the Chinese company Alibaba. They've been pretty far ahead in the development of machine learning methods for the analysis of medical data. So this can save a lot of time because a pathologist needs often 1 to 2 days to go through screens of patients. And to train a pathologist takes a lot of time. And many hospitals are in lack of people with this kind of competences. So to be able to use machine learning to screen good cases from bad cases, and then let the pathologist spend most of the time on the bad cases, is a win-win for all kinds of medical treatments. So I'm not going to say so much more about it. You can look through these examples, and so this is just a way to display the cases you have, and you could actually use these features in the software you find here to look at other data sets. So like in project number 2, we are going to have another data set, and then you could actually, which is still a binary case, and then you could actually visualize the differences between the yes and no cases. And some of the features disentangle this very well, whereas other ones, you cannot tell the difference. And this is actually what you're looking after when you define which features classify your data. Any questions? Does this sound reasonable? So actually, this visualization of the data is something which is very important in us choosing a specific algorithm. There is I'm going to skip some of the things here, but there's also another way of presenting the data, which we will discuss a lot. And one of these is actually called, so this is again, logistic regression applied to the same data set, which you saw now. But in this case, we are looking at some other metrics. So scikit-learn again has lots of metrics, and one of the metrics, which is pretty common, is something which is called the confusion matrix. So let me just show you that one. So, and you will see another thing, that it complains, scikit-learn complains that the number of iterations in your gradient descent are too few. And you probably noticed that in project 1, that you need quite many iterations to find a stable result. So this is a parameter which is set by default, I think, to 50 or 60. So you can increase the number of iterations. But you see now that it's producing a lot of fluff here. So this is something which is called the confusion matrix. So this will be true, positive. So this would be the case where you have yes cases, and you predict correctly the yes cases by 98%. The column here would be true negative. So you're actually making a false prediction of true cases. Here you have a false negative, and this is true false. So these are ways to classify your data. So if this is a yes case, you predict correctly 98% of the yes cases and 93% of the no cases. So sometimes you don't have a balanced data set. So if you have ideally 50-50 of yes and no, you have an equal amount of training data for the yes and no cases. Many of the data sets are what we call skewed. You have less yes cases and more no cases, or the opposite. And then if you have many cases of one of the outputs, yes and no, 1 and 0, true, false, then the training is obviously better. And this is something you have seen in project 1 as well. The more data set you have, the better the training. So sometimes you will find a difference between the true positive, which in this case can be yes, true negative, which can be no, or a benign tumor, malignant tumor, etc. Okay? Yeah.
Is it also important to notice that sometimes you want to adjust your model to get a specific variance of true false positive?
Yeah, that's correct. That's correct. Yeah. We are coming back to that a little bit later. So this is important actually. So now I just wanted to mention some of the measures you can use in displaying your results. And like this one is pretty intuitive, and it tells the reader a lot about your data set. There are some other ones which we'll come back to later. But I wanted to show you the examples. I had some further examples here. Now I wanted with the XOR gate. I just need to remind myself where I put it. Yeah, these are the XOR gates, which the OR gate, the XOR gate, and the AND gates. So the OR gate, which is this one, the first case here, where I've encoded the design matrix, and then I just perform standard linear regression with ordinary least squares, as we discussed before the break. I do the same with this XOR gate, and I do the same with the so-called AND gate. I think this was the AND gate. Yeah, this is the AND gate. So when I run these specific cases, what I will see is the following. So this is the design matrix transposed times X. So this is the matrix. And then I take the inverse, and then I find the values of theta for the XOR gate, for the OR gate. And the XOR gate is a difficult one. So in the prediction which I want for the XOR gate, I wanted 0, 1, 1, 0. But now I'm failing. So I'm just getting 0.5, 0.5, 0.5. If I take the OR gate where we could separate the planes, if you look at this line, I could say now that for a value below 0.5, I put it to 0. Above 0.5, I put it to 1. Then, if I take the AND gate, which is also a case of a separable gate, then I can actually use linear regression. If I now say that if it's below 0, I predict 0. If it's above, no, actually this should be 0, 0, 0. So if it's below 0.5, I predict 0. If it's above 0.5, I predict 1, because these are the outputs for my linear regression. So for an AND gate and an OR gate, I can actually make a pretty good prediction by linear regression. Whereas the XOR gate, which you remember before the break, we could not separate the planes. This method fails miserably. And just to quickly remind you of that, so let me just bring it back again here in the on the whiteboard. So the typical OR gate, which we discussed, is one where I can have 0 here and 1, 1, 1. And that means that I can always find a line which I can define to separate the different classes. We have 2 classes only, 0 and 1. So this is 0, as we said, the crosses, and the circles represent 1. Then what we did essentially now was to set up a linear model of this type here, where we have 2 unknown parameters, and then the weight B. We have 2 features, which are x1 and x2. These are the 2 inputs. I set up a intercept here. And what I'm doing now is to fit a linear model. And this is the linear model which if we go back a little bit, this is the linear model which I'm fitting. Ordinary least squares. Then I have this nastier gate, which is the XOR gate. And in this specific case, you see now I cannot find a plane or line which separates well the different cases. Whatever way you draw the line, you cannot separate them. And you saw that the output was just wrong. It just predicted the same output for all the 4 cases. So this is a case where linear regression fails. Similarly, we could repeat this exercise with a logistic regression. So if we do logistic regression, what we would have then would be a model we would train where we have a probability distribution of this type here, of this one. But instead of only theta 1, we have a theta 2 as well, multiplied with an x of I. And then we train that model. So you could take that code I wrote with the gradient descent, or you can take logistic regression and from scikit-learn and run it and see what you get. So let's go back to the Jupyter notebook and see what happens if I run the same case with logistic regression. So what I would do then is to define these gates. So this is the design matrix with the intercept here. You see the ones here. And then I have the cases with bits 0 and bit 0, bit 0 and 1, 1, 0 and 1, 1. I print again my standard case here with the linear regression. But then I do the same thing with logistic regression. And the only thing I feed in now is the design matrix. I have my output for an OR gate, an XOR gate, and an AND gate. So if I run that one, what I'm going to get then, if I look at logistic regression, so what I say now is that the accuracy for the OR gate is 0.75. The accuracy for the XOR gate is 50%. So this is just like tossing a coin. So a logistic regression is not able to actually predict the XOR gate in the same way as my linear regression did. Yeah. For the AND gate also, yeah. No, because the AND gate, if you look at that one, so let me just, I can just bring it up here because I didn't show that on the whiteboard simply because of time. But let me just bring up the AND gate. So if you look at the AND gate, if we now go back here, if you plot that one, so this has as inputs x1, x2, so you have 0, 0, 0, 1, 1, 0, 1, 1, and then the output here is now 0, 0, 0, and 1. If you plot it, like we did previously, so we have 0, 1, and then we use crosses for the zeros. You have a cross here, and cross here, and then the circle for the ones. You see now that you can draw a straight line which separates the cases. So here, a linear fit does a job for you. The only thing you have to do is to define the threshold value. And logistic regression does pretty well here as well. So what we are going to do now is actually to introduce neural networks, because neural networks can actually do this fitting for us. And that has to do with the fact that a neural network brings in a nonlinearity which you don't have in logistic regression and in linear regression. So let's go back to the Jupyter Notebook first, and then take a quick look at what a neural network is doing. So scikit-learn has a very simple neural network code machinery. There's one for regression cases and there's one for classification. So what I've done here is to use this multi-neuron or multi-perceptron model, which is called the MLP classifier. So I'm setting up the classifier. I set up the max iterations. I give my X value and my, this is the design matrix, and this is the output, which is that one for the XOR gate. And if I run that case, I'm going to make a prediction here, an accuracy which is exactly equal 1. So that means it makes a perfect prediction for all the cases I have, all the 4 cases. Now, if I wanted to train this data, and these are some subtleties which you will encounter when we discuss project number 2, you could actually just increase the data set which you have because you have 4 cases. You could just duplicate it. So you can just duplicate it, and then you have 8 cases, 12, 16, and so on. So remember now that you have bit 0, 0, 0, 1, 1, 0, 1, 1, but there's nothing which hinders you in duplicating this one and then just have more training data. But that is pretty common. So you will see that when we start with the project number 2. Any questions so far? So when we go back to neural networks, so what I wanted to say now, there are several things which we will cover. So the first type of network we will cover, which is the task of project number 2, is a standard neural network. That's a feed-forward neural network. And I will try to explain to you what these names actually mean. And The next case we are going to look at, which is the huge success case of deep learning, and that is about convolutional neural network, which has played an amazing role in image recognition. So that's something we will discuss the mathematics of, but the implementation is something which we will use with PyTorch or TensorFlow. Because if you want to write your own convolutional network code, that is a one semester project. And then we have recurrent neural networks, which we will also discuss, but we will use the ready-made libraries which we have from TensorFlow or PyTorch. So recurrent neural networks are actually the cornerstone in language models. It's the starting point for making your first large language model. But for me, who does analysis of time series, it's also one of the methods of choice. So these are the three main methods we will discuss when it comes to deep learning. So deep comes simply from the fact that you are going to make a network which has many hidden layers. The more hidden layers, the more parameters to train, the deeper the network. So deep learning means that you're training something which has many layers. Okay? So when I say deep learning, in this course, we will mainly look at these methods. If we get some time, I will say something about autoencoders, but we will see where we are towards the end of the semester. So the type of system which we are going to look at now is something which is called a feed-forward or multi-layer perceptrons. There's a very important thing here. And I'm going to put that one in the notes next week in more detail. And that's called the universal approximation theorem. Now, if you look at that case with the XOR gate and the OR gate and the AND gate, you could actually make a prediction by fitting a line which separates the cases. But you saw from the XOR gate that you could not make a well-defined line which separates the cases. This is an example of a case where you need a non-linear approach. So the universal approximation theorem, and this is what made neural networks really take off in the beginning of the 90s, was a theorem by Sybenko and then Hornig, which simply says that you can fit any non-linear continuous function with at least one hidden layer. That's an amazing statement. But you can fit it to a given precision. You don't know how big the network needs to be and what the precision will be, but you can fit any non-continuous, non-linear function with a neural network with at least one hidden layer. So the theorem itself is a tour de force in real analysis. Yeah. Could you just speak a little bit louder? So you're thinking of fitting data, right? No, you would typically start with one hidden layer. If you then get 100% accuracy in a classification problem, there is often no need in going to a deeper system. Because what could happen then if you make the layers, the network deeper and deeper, you can easily end up in a region of overfitting. So think of, because now the important thing for us to think of is that the architecture of the network is our model. So think back now to what we did. So logistic regression is basically this. So we are feeding in some data, and you saw we had these weight parameters, and then we have a function here, which then spits out an output. Okay, that's essentially what we did with logistic regression. And then we compare this output with a cost function and the target values, and then we optimize this cost function. So this, in a way, what you see here encircled and in the box here, that is our model. And you can think of linear regression in a graphical way, ordinary least squares, in exactly the same way. So you make a model, you spit out an output, and you want to compare that one with the target values. So here in this figure, which I stole from another textbook, we have been using Y tilde here. Now, when you then make a neural network, pay now attention to the following. So we have the input layer as here. This is also the input layer, what you see there. But then we have a hidden layer where we have some unknown parameters, which are the weights, normally called weights. And there is also a so-called bias parameter, which here played the role of an intercept. But here it becomes a parameter which hinders that a given node, so every node here is also called neurons or units. Every node here has an activation function, like the sigmoid, which we mentioned. So that means you get a set of parameters. So if I have 100 inputs and 100 nodes, I have a matrix which connects all these nodes, which is of dimension 100 times 100. So that means that for this layer, I have 10,000 parameters to fit. If I then continue with a new 100 nodes here, I would then have a new 10,000 parameters. Now you see that this can grow quickly when it comes to the number of parameters. So in project number 1, you had perhaps polynomial of degree 10 parameters, and then gradient descent meant that you just did gradient descent for 10 parameters. Here, for every hidden layer with 100 times 100, you would have to have a gradient descent for 10,000 parameters. And then the next layer, another 10,000, et cetera, et cetera. So you see that the number of parameters can grow quickly. And the thing is that the output layer, which is this one, in the case of the yes and no, there is only one output. And that was given by, let's say, yes or no, or 1 and 0. If you have a multi-class case, like this 10, 100 numbers, which you want to classify, then you have 10 outputs, a probability for each one of them. If you're looking at a function value, so suppose you want to fit a function, because you can use this to fit a function, you can use it to do a classification, then the output is just the value of the function with that input. Does that make sense? So now there is, I'm just going to say this with words, but we were going to restate it next week. So what you have here, this is the architecture of the network, and that is your model. So the model here is defined by the number of hidden layers, the number of nodes, and the type of activation function which you're setting up. Then, so the model now is defined by hidden layers, the number of nodes or neurons, as we call them. So this is very much inspired by neuroscience. The type of activation function, which is this F here in this figure, that is also part of the architecture or the model. So when you set up a polynomial fit, your model was the polynomial degree, the complexity. The complexity now is defined by the hidden layers, the number of nodes, the activation function, but it has also other ingredients. And what we are going to discuss next week in more detail is how we train these parameters. And there is an algorithm which is called backpropagation. So it's called a feed-forward network because you are going to feed the input through the network. That produces an output. That output is compared with your target data. Then you calculate the gradient of the cost function for the output. And then you start calculating the gradients of the other parameters to train the network. And that's called backpropagation. Backpropagation is you setting up the gradients using the chain rule, essentially. So this is going to end up with you doing the chain rule and performing matrix vector and matrix multiplication. That's the essence mathematically of a neural network. So the backpropagation is just an algorithm where you use the chain rule. So if you want to be very arrogant, very arrogant, you could say this is fairly beyond high school mathematics, where you went through the chain rule. And then when you came to university, you got some linear algebra. But this is an extremely arrogant statement. So don't quote me on that. But essentially what you end up in practice is to implement the chain rule, set up the derivatives, and then perform the right matrix vector operations. And this is something which always leads to some errors because we can interchange indices easily. So the exercises which are going to come in the next weeks, they're actually going to start with scalar inputs, scalar output, vector input, vector output, and then matrix input and matrix output. So that we can really step you through all these technicalities. And then on top of this, and this is where we're going to stop, you're going to have the gradient methods because you need to update the parameters. So all these parameters you see here, the weights, are going to be updated with gradient descent because you're calculating different derivatives by the chain rule. And finally, we have hyperparameters, which you had in ridge and lasso regression. So that's the, the bird's view on a network. So the model is now the network architecture. And when you think of overfitting bias variance trade-off, you would then test it as a function of layers and as a function of nodes. So you can have a perfect training with one layer, you increase the complexity, and then you start overfitting. But you don't know that before you start doing the calculations. So this is the kind of bird's view. And then next week and the week thereafter, we're going to go through all the gritty details which you need in order to write your own code. We stop here, guys? Okay. Have a great week.